Hello, everybody. Good evening, and you're very welcome to the MIT Museum, where our mission is to welcome all to participate in MIT's unique culture of problem solving and playful creativity. And I think we're going to hear something about problem solving and various kinds of creativity tonight. We're truly thrilled to have someone with us whose introduction is very hard to give because the numbers change every day. So, one has to kind of keep a live tracker on citations and H numbers and so on. Bob Langer is Institute Professor here at MIT, one of 9 Institute Professors. This is the highest honor that can be awarded to a faculty member here. He's written over 1,600 articles as of this afternoon, and these have been cited 442,000 times. He has an H index of 330, which is the highest of any engineer in history. And it's also the 6th highest of any individual in the world in any field. That must be a little bit annoying to be 6th highest.
I'll take it.
His patents have licensed or sub-licensed to over 400 companies. He's a co-founder of a number of companies, many of which you will have heard of, including Moderna. So, Bob, so wonderful to have you with us at the MIT Museum this evening.
Thank you for having me.
And it's been estimated, I don't know exactly how this was estimated, that over 2 billion lives have been directly affected by Bob's technologies and the technologies invented by his research team. So pretty extraordinary. And some of the topics we'd like to dive into this evening would include the cross-disciplinary approach that has been characteristic of your work and the work of your lab. Also, how innovation, persistence, and translational impact have been key themes through the work of Bob Langer, and also to look to the future of what's exciting right now in the Langer lab, but also for biomedicine more broadly. And there will be an opportunity for you all to ask questions, so please think of questions that you might like to ask Bob this evening. It's a really special chance, and we'll have a microphone going around the audience. So, Bob, if I may, I would love to start with your childhood and to go back to Albany, New York, where you grew up, and to ask you if you can remember what it was that first gave you the spark of interest in science.
Well, when I was a little boy, there was this company called Gilbert, and they made like erector sets and microscope sets and chemistry sets. And I got some of those as gifts, and with the erector set, I remember you could make a robot and make a rocket launcher, and with a microscope set, you could watch like shrimp hatch. And with the chemistry set, I always liked magic. I still like magic, and you could, mix chemicals together, and they change colors, and all of those things. I think those sets were great. I think probably a number of people my age use them. They don't have them anymore, but they were great, in terms of getting me interested in all those things.
And did you have a parent or a teacher who was particularly encouraging of these pursuits at an early age?
My dad and my grandfather would play math games with me, and that I liked. I could count pretty high even when I was very young, but not really. They just bought those sets, and when I was a little bit older than that, and they were fun, and so I really didn't, other than just my parents getting me those.
And then you made the decision to apply to study engineering in Cornell. What led to that choice?
Yeah, it certainly was not anything very deep. When I was in high school, I was good in math and science and terrible in everything else, like French and English. I was a disaster in. And my father and my guidance counselor said, well, if you're good in if you're good in math and science, you should, major in engineering or apply for engineering. And really, I was so dumb. I honestly thought engineering ran railroad cars, and I didn't understand why that was going to be, math and science would be so useful for that. But anyhow, I applied to engineering schools, and I ended up going to Cornell. But it really was not very well thought out.
But then you discovered chemical engineering as a
right. That wasn't well thought out either. But my first year at Cornell, I did terrible in physics and most everything except for chemistry. And I like chemistry. I've always enjoyed chemistry. And that was the one course I enjoyed and the one course I did well in. You had to decide by second term what you were going to major in. So, I picked chemical engineering.
And then tell me about the journey to MIT. How did you end up here? And you came to do your PhD here. How did that happen?
Yeah, well, so I like I said, I went to Cornell and majored in chemical engineering. As I would get done, I didn't really have a very clear idea of what I wanted to do. I didn't even understand that much about what chemical engineers did other than, maybe oil wells and things like that at that time. But so I thought about applying to graduate school really to postpone things. I did get a couple jobs to run chemical plants, but that would have been a disaster for the chemical plants. So I knew that. I knew I was, I'm still a terrible engineer in terms of practical things. Yeah. My wife thinks I can't, screw a light bulb in, and she's not wrong. I'm just, I keep asking her to fix things. But at any rate, so as I finished Cornell, I thought, well, I'll apply to graduate school. Maybe that'll help me figure out what I'll do and also postpone the decision. And so I applied to graduate school. One of the things that appealed to me, and I should say, I wasn't really sure. I did fortunate enough that I did okay at Cornell, that I got into some pretty good schools. I started out doing terrible again at Cornell my first 3 terms, but eventually I did okay. And so I got into a number of schools. So MIT was one of them. And what I liked about MIT was the chemical engineering department, which was my major at Cornell. It was diverse, and you could pick different, they had like 8 areas. I still remember, like applied chemistry. They did have a little bit about bio stuff, and they had electrochemistry. So I felt, well, since I didn't know what I wanted to do, yeah, there were a lot of choices, and maybe I'd figure it out.
Yeah. And in terms of not knowing what you wanted to do, I came across this quote, which I found quite interesting. It shows some of the, I suppose, the challenges you were experiencing at the time. You say, after the first year or two, I started to think that the research I was doing was not really important. I could not see how it would have great impact or change the world. So it seems that you had a moment when you were at MIT where you were really wondering if you were on the right path at all.
Yeah.
Can you?
Yeah. Well, of course, I was. It's funny when I look at students today. There's so much. I was so naive compared to almost everybody that I see, even undergraduates, and now I'm a graduate student. Yeah. So I didn't really know what I wanted to do. So the idea of doing something in the bio area had some appeal to me, but I didn't know very much about it. So at that time, 1970 to 71, some of the people in chemical engineering and nutrition and food science and chemistry, those 3 departments, they wrote a big grant to NSF, and they got it. It was the biggest NSF grant for what was called research applied to national needs, on using enzymes to synthesize certain things. It sounded, at first glance, since I was, like I say, pretty naive, that it might be interesting and useful. But as I was working on it, I couldn't see, and neither could any of my college students who were working with me, why it would be, at the end, why it would end up being, practically useful. And again, being an engineer, you always, you want to think about something that might be useful. So, and I kept asking some of the professors why it would be useful, and they really didn't have an answer other than they got the money. And that was kind of disappointing to me. And, and of course now we're, 53, 54 years later, it still hasn't been useful. So I don't think it was wrong. But so that just, I just was always hoping if I was going to do something that it would help people or that it would do some good. So, and there was I remember my classmates, Bruce Hamilton, he kept, asking that question, why is this going to be good? And like I say, people really never had an answer.
Yeah. I was really interested at that time, you got involved in this project to create a school for high school dropouts here in Cambridge and in Boston. Can you maybe tell us a little bit about that? Because that seemed like a fascinating project, the group school.
Yeah, so, well, anyhow, my last year at Cornell, which was, the spring of 1970, I was a teaching assistant for a course in heat and mass transfer. And I really loved that. I just felt like I just loved working with the students. They were just a year younger than me, and I really enjoyed it. I felt like I was able to explain things well, and many of them would come up to me afterwards and said, it just was incredibly helpful, which makes you feel good. And so when I came to Cambridge in 1970, I thought, and of course this was a time, as people might remember, when the war was on and the Vietnam War, and I think a lot of protests, a lot of people were looking to do different things. And I thought, well, education, that's something that would be a really good thing to do. And so at MIT had a couple of programs. I think one was called Urban Action, which was an MIT program, but Cambridge itself had many programs like Education Warehouse, where you do tutoring. So I talked to them, and actually Bonnie Kellerman, who's still here at MIT, she was, I think, the vice president or second, in Urban Action. And so, anyhow, I got very involved in tutoring different people in Roxbury and Cambridge. And again, I really liked it because I felt like I was doing some good. I felt people were learning. And so, anyhow, so I did that. But then I guess there were several people, Peter Haggerty and Neil Diedrichson and Barbara Gates, and they were starting this school called the Group School. But they were all like in humanities and things like that, more from Harvard. And so I guess they had talked to people, and they heard I was okay at like teaching math and science. So they said, would I come and help? And so I did. And then, we started the school. Cambridge, people probably don't realize this, but in 1970, 71, Cambridge had the highest high school dropout of any city its size in the country. It was 35%. And there were these projects, Jefferson Park and Roosevelt Towers not far from here. There was a lot of delinquency and crime and so forth. So at any rate, the idea was, but Cambridge, but also we started the school also. I'm trying to think how to say that. The people at the school, they were very liberal. I mean, Cambridge is liberal in a lot of, well, some of the people in Cambridge, very liberal to begin with.
Republic of Cambridge.
Right. Yeah. But here, their attitude and the students would play a big role in the governance, which was part of what they did, and part of how they set it up. So the idea was, well, you could have math and science, but nobody had to take it. Yeah. But it was there. It wasn't a requirement. Mm-hmm. So at any rate, but I was like the only person doing that. So I spent a lot of time trying to figure out how to make math interesting and fun. And I still remember the first year, since nobody had to take it, I think 4 or 5 people took it out of like 37. Yeah. And chemistry, of course, we had no science, but I got MIT. Louis Manan was the associate provost, and I talked to him and some other people, and I got a grant to create a chemistry program with 2 undergraduates, David Sincata and Kathy Cole. And we wrote this curriculum. And so anyhow, the next year, we did a couple things. We had the math program. Mike Riley, who had graduated from MIT in 1979, he got interested. 1969, he started helping me, and we started this math program. And actually, that year, because I think what we'd done was successful, 45 out of 50 people took it. The school expanded.
So maths was a hit.
What's that?
Or chemistry. Was this chemistry or math?
No, that was math.
Math, yeah.
And chemistry, quite a few people took it, and they liked it, So
amazing.
I felt like we were doing some good.
Yeah. And then you energized by this experience, you were interested in, could you develop chemistry curricula in colleges? I believe you went to apply to City College in New York and.
Yeah, that didn't go so well, but but it did. One of the things that I saw when I was at the school. You always look for how you could have an impact. And I, I had certainly noticed that if you were a professor, you could have more impact on a high school students in a way, and I'll give an example from MIT in a second, than you could if you were a high school teacher. With a high school teacher, maybe I could affect 50 kids, but I was hoping I could do something that might affect more people. And what I noticed was when I did this, there was a MIT professor, Harold Zacharias, and he wrote a physics book, and everybody in the country started, or lots of people in the country started using it because he was here, and it was probably pretty good. But at any rate, so it seemed to me if you could do something like that, then maybe you could have an influence. To take a step back on jobs, I mean, the first thing I thought about, because I'm pretty good at not knowing what I wanted to do. Yeah. When I was finishing my time at MIT, almost everybody, this was now 1974, almost everybody in chemical engineering would work in the oil industry. If you were at MIT.
So this was the time of the gas crisis, right? There was
the
Yom Kippur War.
What happened? So what would happen is if you had a car. Actually, this is true. If you were at a car in Cambridge, in 1974, you had to wait in line to get your tank filled up for about 2 hours. It was, pretty bad. At any rate, so pretty much. Again, since I didn't really know what I wanted to do at first, I thought everybody else, all my friends, are applying to oil companies and getting jobs, and it seemed to me like, well, probably I ought to do the same thing. Like I say, I was still such a naive person, so I did, and actually it was interesting. I'm almost embarrassed to say this, but when I was 24 years old, as a graduate student, I had not been in my entire life east of Boston or west of Buffalo. So now for the first time, I'm going to all these places, Houston, California, Tennessee, for different job interviews. And it was interesting. Actually, my wife would tell me later, she's, finding a job, that's like a full-time course. And certainly for me, it was probably for 2 terms. So I'd go to these places, and they did offer me jobs. And like I say, I wasn't that good, but, they.
But oil industry or.
Well, oil industry was the most of it. Yeah. Some of them were chemical companies, but almost everything was Exxon. I got 4 offers from different Exxons, and they were in Baton Rouge and Baytown, which was near Houston, and then in New Jersey. And Shell and Chevron, they'd all offered me jobs. But like I say, it wasn't because I was that good.
But that must have been a very attractive thing to be offered these.
Well, it's funny jobs. How you look at it. I was. Maybe I wasn't that smart either about this. I wasn't very concerned about money. They offered you a lot of money. But it's funny, when I look back at my life, it's probably almost, again, embarrassing to say, so when I was an undergrad at Cornell, I think I was, I lived in a $60 a month apartment, came up to MIT, and I had maybe shared, had roommates and maybe spent $100. And I think I had a stipend of $240. So the amount of money that I was used to spending was very, very little. So even when I got this postdoc job that paid me maybe $1,000, which was nothing, $1,000 a month compared to the oil companies, which were several thousand a month, I saved more money proportionately than I ever did in my life. So, because I just wasn't used to spending money. So at any rate, I just wasn't, it just didn't matter to me that much.
That wasn't your driver.
It really wasn't. I kept thinking, what did I get satisfaction out of? And my dad and mom, they were very, my dad was a small business owner. He ran a liquor store. My mom was, took care of me and my sister. They kept saying, we just want you to be happy. So they didn't think, being rich or anything wasn't important. And that's what I felt. I got a lot more satisfaction out of doing, and I didn't know what I'd really wanted to do. But what was interesting is I'd go to those oil companies, I kind of got an idea what I didn't want to do, which I tell my students. I was just talking to one of my students today about job interviews are really good because she kept telling me, well, everything she's done told her what she didn't want to do. I kept saying, that's good.
That's a valuable experience.
Yeah. Right? So anyhow, but I decided after really all these different interviews that I just wasn't going to do that. So then I saw an ad to, like you said, to be an assistant professor at City College to develop chemistry curriculum. So I wrote them a job, but they applied to, but they didn't write me back.
Where's City College? And
Well,
then you wanted to write chemistry curricula. You applied to, I believe, a number of other places, and
yeah, they wouldn't write me back either.
Yeah. Nobody wanted you to teach chemistry.
Well, I think I think people, and I still think this is true in so many ways. People want you to be in a certain box, right?
Yes.
There's departments of chemistry education. There was Journal of Chemical Education. I wasn't in that box. I'd majored in chemical. I thought what I'd done at the group school was really important, but they certainly didn't think so. And so I just wasn't in the. I think you have to sort of be in the right box for somebody to want to hire you.
And then somehow you made the leap into a very different box, right? The biomedical box. So how did that happen?
Well, so the good thing about first figuring out I didn't want to work in an oil company, and then figuring out that I did want to do something that helped people, like teaching, I started to think of other ways I might do something like that. So I thought about medicine. So I wrote to a lot of hospitals and medical schools, and they didn't write back either. But then eventually something good would happen. So finally, at the end, what happened was one of the people in the lab where I was said to me, after all that, he said, well, Bobby said there's a surgeon named Judah Folkman at the Children's Hospital, and maybe he sometimes he hires unusual people. And so I wrote to him, and he was actually called me up and ultimately offered me a job.
What did he see in you that others hadn't?
I guess he said, well, he had this idea that if you could stop blood vessels, that might be a way to someday stop cancer. Mm-hmm. And actually, I mean, it turns out it was quite a and he also thought that it was chemically mediated by something he called TAF, or tumor angiogenesis factor. He said that he'd hired different people to work on it and work on it himself that had maybe more conventional backgrounds, and that hadn't worked. So he was I guess when he looked at my CV, I'd won certain awards and things like that, and he thought he'd take a chance.
And you then got stuck into this angiogenesis problem, the problem of how to prevent blood vessel growth. Can you say a little bit about that and that collaboration with Judah Folkman?
Yeah, well, I was a postdoc with him, and he had, and
this was at the Children's Hospital, right?
Yeah, yes. Yeah. So the immediate problem, was having what's called a way to study blood vessels growth. Mm-hmm. And that's not so easy because it's hard to be even somewhat quantitative, because wherever you go, there's often background blood vessels. A couple places where they're not if you look at a chicken egg that grows, there's a membrane on top of it, if it's live, called the chorial membrane. So it has very sparse blood vessels. And then if you have a cornea, there's no blood vessels. So, Mike Gimbroni had been there before me, and he had put tumors in a cornea, and that would cause blood vessels to grow. So what Dr. Folkman and I talked about was maybe we could create a little pellet, mm-hmm. nanoparticle or microparticle or something like that. If we could isolate something, and cartilage, Henry Brem had done some work on cartilage, and if we could isolate something from that, maybe that could stop blood vessels from growing. Problem was all the molecules in cartilage were big, so we needed a little particle to be able to deliver big molecules, and like proteins or...
This was where the first ideas emerged around using nanoparticles to carry macromolecules, was it? Or was this...
Yeah, well, they were... again, what we did is we created the polymers were tiny. You could make mm-hmm. them into nanoparticles or microparticles or little pellets or really anything. Mm-hmm. So, we tried to do that, and of course, people didn't think you could do that. At that time, there was really only one company in the world, really, I guess, working on advanced drug delivery systems, which is a company called Alza, just in Palo Alto. Mm-hmm. They would ultimately make now transdermal patches and other things, but they were all for small molecules, and so And they had a very prestigious advisory board. Paul Flory was on it, who was a Nobel laureate in chemistry, and they had a lot of great people, some from MIT. And so Dr. Folkman asked them about that, but they didn't think it was possible to deliver large molecules. So but if we were going to solve the blood vessel problem, we had to address that problem first.
Yeah. And then out of that emerged your first Nature paper, which was, I think, 1976. Which
That's
was
exactly right.
With Judith Folkman, and which was publishing this discovery. But then tell me about how you then went about thinking about how to fund this research further. You
How to fund it?
Yeah. How to fund it, how to really build on this research. You were at MIT, you were in this moment also, I guess, of the beginning of the biotech revolution here in the mid-70s. It must have been a really exciting time around Kendall Square, and must have been the beginning of that whole story, right?
Yeah, well, when I got to MIT...
Just before Biogen arrived, I suppose. Yeah.
When I got to MIT in 1977, I didn't have any grants. I tried to get grants. My first 9 were rejected. I did terrible, actually. But I kept writing.
9 rejected grants?
9 straight, yeah.
Were these federal or...
Mostly federal, mostly NIH or NCI. I mean, but it was hard. What happens is I'd get them reviewed by, there was what's called the pathology B study section. And I think they didn't think chemical engineers do very much. I mean, that's what they said, So I didn't, again, that's being in a certain box. I wasn't in the right box. So they keep saying I didn't know anything about biology, which is probably true, but so I didn't get, in fact, the way I funded it for really the first year was maybe a little bit embarrassing. MIT had this UROP program, and what I noticed is that if you had a UROP, and again, if you had, for every UROP student you got, they'd give you like $400 to pay for things. So I had a lot of UROPs. I had a tremendous number of UROPs, and that really would make a big difference, and they were great.
And you struggled a bit also in MIT to kind of, you were applying for different roles here, and you had, I believe there was one incident where somebody blew smoke in your face.
Yeah. well, yeah, so that's a whole other thing. So again, when I applied, when I got done, well, never maybe really got done with being a postdoc, but at any rate, when I started, I was at Children's, full-time for 3 years. When I got, a lot of my friends said, I shouldn't probably be I could have stayed there. I loved that. I learned so much, and I had a lot of friends, but people would say that I should probably do something, permanent. So I applied to chemical engineering departments. No chemical engineering department in the country would hire me. Because again, what I was trying to do didn't fit with them. I was trying to, there were a few chemical engineers doing bio stuff, but it was all kind of mathematical modeling, like transport through kidneys, things, or cells, and I wanted to make things, do experiments. So I didn't get any. But Dr. Folkman introduced me to Nevin Scrimshaw. Nevin Scrimshaw was head of the nutrition department. And Nevin Scrimshaw, if anybody remember, I mean, he was what I'd call a benevolent dictator kind of department head, meaning that he did what he wanted, and he hired me, but he didn't ask anybody else in the department what they thought. And so what happened in that case was the year after I joined the department, he left. And so a lot of the senior faculty, they didn't like it. It wasn't just me, but a lot of the senior faculty told me I should leave too. The example that you're saying, this was a whole other thing that happened in the nutrition department. So he left, and now we're maybe a year later. One of the things I'd noticed is that maybe around 1979, I was, junior faculty. So the senior faculty, they decided that they had this thing that they should do, which was to ask they should have events where they'd get to know the junior faculty better. And they would have so once a month you'd have to have a seminar by a junior faculty person, and then they'd have a nice dinner. So my friends like Alex Klebanoff and Mike Marletta, we were all the youngest guy, So we'd start to notice, like, every time they had the seminar, the senior faculty, like, they just ripped into the young professors who were, because we were assistant professors, they were all associate professors without tenure. They'd just give them a really hard time and ask them lots of hard questions. And then none of them got tenure. I mean, it was amazing to see that. So at any rate, when it came my turn, I gave this talk. Again, there was a dinner, and then Mike Marletta, who was one of the people I mentioned, he has this quote which he once gave when he was giving a dinner speech about me, which is a true story. I was, after the talk, one of the senior faculty members at the dinner, he blew a cloud of smoke in my face and with a cigar, and he said, well, you better, if this drug delivery stuff you're doing isn't worth anything, and you better start looking for another job.
Wow.
So I had not the best beginning.
That's pretty harsh. But then you...
Well, by the way, MIT in the old days was a lot harsher than it is now.
There was no belonging or any of
Well,
this,
it just was a very different time. There's a story in chemical engineering. I probably shouldn't say this, but I will. The most famous chemical engineer was a guy named Warren Lewis, and he was really responsible, I think, for building the chemistry department. I remember, somebody telling me this story that, there was this class he was teaching, and he'd ask people to come to the blackboard and answer questions, and if they got it wrong, he'd spit on them, and he'd keep spitting on them until they got it right. And they'd give people just a really hard time, like in the doctoral qualifying exams and everything. I mean, there was this enormous fear of a lot of these professors. I mean, this was the 1970s. In fact, just another quick story, which I probably shouldn't say, but I will, is that I don't know what it was like at biology field, but anyway, in chemical engineering, now I'm going to go back to being a graduate student in the early 70s. So you had a doctoral qualifying exam, and you had to give this 10-minute talk on something in science. So I wasn't sure what I was going to do, but the one experience I had as a summer job that I thought might be helpful is I was working on making a battery at General Electric, mercury zinc battery. So I thought, well, I'll give the talk on the battery. And so I noticed, I was looking at this, they had the students give seminars every Friday, and they all were half an hour, so it was longer than that. But I thought and one day I saw there was a student named Ogden Hammond. He had graduated from Princeton, and he was giving a talk on batteries, and I was so excited about this. I'm going to go to that one, and then I'll know just what to say. So he gives this talk, and it was okay. I didn't understand everything, but I thought it was all right. Anyhow, what they did at the time, this was now 1971, the graduate students, they had 2 graduate students who were supposed to evaluate it at the end. And so anyhow, he'd give the talk and then answered questions. Some of the professors would give him a hard time on the questions. But anyhow, I thought, well, that's okay. So anyhow, the first graduate student gets up and says to him, Ogden, I just want to tell you that I've been coming to these seminars for the last 3 or 4 years. And this was the worst seminar I've ever heard. And he said, that includes the one you gave last year. But it was just really a very, it was so surprising to see what MIT and chemical engineering was like then compared to now.
Wow, wow. But I'd like to maybe move on a bit to, in terms of, you mentioned that you'd had multiple rejections from federal grants and so on. And this led to you really looking at how you might engage private industry to support your projects and to support your research, and to pursuing patents and licensing and so on. Can you talk a little bit about that moment and the way you kind of made the Langer lab ultimately into a kind of a factory for new companies and
well, that took sure. Well, that took a while. Eventually, I did get some grants, but it took a while. Even NIH grants, and I actually for a while did pretty well that way. But still, when you come up with new ideas, a lot of times I wouldn't do so well. So, but anyhow, as the 80s came, I started getting grants, and I got a reasonable number of grants from NIH and NSF. But still, I'll just pick an example to illustrate, because now you're asking about the companies. One of the ideas that I had along with Jay Vacanti, who was a surgeon, was that maybe we could use materials and cells and make new tissues and organs from scratch. And we wrote grants to the NIH, and again, they ridiculed it. I mean, and we didn't even come close. I mean, there's like there's something approved and not funded. We didn't even get that far. You just get rejected. So we did write patents on it, though. And so what happened in that case is we filed patents, and like I said, we wrote a number of grants, and we didn't get them. But now it must be maybe 1988, and Lita Nelson and John Preston were in the patent office at that time. Actually, I'd had other experiences where we'd also licensed patents, but not necessarily always to get grants. But there were a few, and I'll mention. So that was one example, and we wrote the grants, and we got venture capitalists to give us the grant, and then we'd use those grants to hire graduate students and postdocs. In fact, Linda Griffith was one of the earliest of those postdocs, and David Mooney, who's now an associate dean at Harvard, was one of the earliest graduate students. I mean,
Linda was also very involved in the tissue engineering.
Yeah,
the mouse also.
Yes, well, we work with it.
The Vacanti mouse. Do people know the Vacanti mouse? The mouse with the ear.
That was Jay's brother Chuck, and Linda worked with him.
Probably one of the first internet sensations. It was, I think, in 1996. It went viral. This image of this human ear on a mouse.
I wasn't crazy about that, but the BBC came, and Jay would always have arguments with his brother about what to show and what not too. So the BBC wanted to do this show, and they came, and on my case, all they did was show me running on the Charles or something, but they did show that. But that was kind of, I thought, embarrassing, but you're right, it certainly was an internet sensation. Other ones, we also, I had ideas on creating new materials, and this goes, and then Sal Snyder had a company called, this is now back in the 80s, called Nova Pharmaceuticals, and I had these ideas on creating, one of the things, again, that I had thought about working in the hospital was, people, I was curious, since I'd worked on materials, how did materials find their way into medicine? And I'd start noticing all the materials that were used in medicine up till that time, they were always driven by medical doctors, and pretty much they'd always go to their house to find an object that resembled the organ or tissue they wanted to fix. So if you look at this, take the artificial heart, that was actually Bill Pierce and others, cardiovascular people in the 1960s saying, well, what would make, has a good flex life, and they picked the lady's girdle.
The lady's girdle.
And that's what they made. That's still, that material, the polyether urethane, the lady's girdle, is what the artificial heart's made out of today, because once you start down that path, it's not so easy to change. Another example that I noticed was the breast implant. Some of those were mattress stuffings. And I just thought that's where so I thought being a chemical engineer, rather than just take things from your house, you could maybe do design, ask the question, what do you really want in a material from an engineering standpoint, biology standpoint, chemistry standpoint, and synthesize it from first principles.
From the ground up.
Yeah. So from the ground up. So I had different ideas on materials we could synthesize that might have much better properties than pre-existing ones and be degradable and so forth. So I wrote grants on that, and again, the NIH wouldn't fund it because they said it didn't make any sense, and it got rejected many, many times. But Sal Snyder had started this company called Nova Pharmaceuticals, and it was amazing. I mean, Phil might remember this much better than me, but in the early 80s, there was a lot of venture capital people coming, and here's a company, they funded him, but they didn't really know what they were going to do, but they just had a lot of money. So they came up and saw me, and they said, we want to fund something. I said, well, what did you want to fund? And he said, well, just something that you're doing. Yeah. So anyhow, I thought, well, since they were in Baltimore, I said, well, I mentioned one of these polymers that we were studying to maybe be used in brain cancer, and we were collaborating with Henry Bremer was a friend of mine that I'd met in Dr. Folkman's lab, and he was a young neurosurgeon there. Now he's neurosurgeon in chief there. And I said, yeah, well, maybe you could fund us and fund him. And so, yeah, but that was another way. So we got grants from companies, from the patents, and grants from, startups that, and we've kept doing it.
And you obviously had an amazing mentorship experience yourself with Judah Folkman, and you have also mentored and collaborated with a huge number of people who've come through your lab as graduate students or as postdocs. Can you, and some of them are probably here in the room, can you say a little bit about your kind of philosophy of mentorship, or is there a particular approach that you adopt to bringing people, for example, from being a PhD student to actually launching their first company?
Well, yeah, I mean, I see David Edwards is here. He'd be a good person, and Joe Salone. But I mean, they could do it better than me. But I think Dr. Folkman was a really good role model, first as a mentor, because for a couple of reasons. One, he believed almost anything was possible, and that was a great thing for a young person like me to see. And the other thing I felt like he did was what I guess I might think of as positive reinforcement. Like I know like people in our lab over the years have worked hard, and I remember people keep telling me, why do they work so hard? They're there all the time, and do you order them to work hard? And I don't. I mean, but I like to think that when from the way he talked to me, I felt like I was working on a problem that would really help a lot of people. And I believe, that was really important, that if you were successful, it would make a big difference in the world. So that's something that I try to impart, to the people who work in the lab, that if they're successful, that could make a difference. And in terms of companies, I'd done that in a few examples in the 1980s, and that would ultimately lead to different products that, again, would help people. And so it seemed to me like that would, so people would see me do that, and I think that they thought, well, maybe they could do that. I mean, David Edwards, who's here, is a good example. David developed a whole new class of aerosols and published in Science, and we had done, even this was 1997 when that paper came out, and so since I'd been involved in starting several companies by then, he and I talked with Terry McGuire, who was at Polaris, and we started this company called Air, but we kept doing it, and so it just seemed it's not easy to get things from the lab out to the world. It takes science, money, really good people at the company. And I don't know that there's any magic formula. It's just that you try.
But you are a keen fan of magic. We should remember this. But I have two more questions for you, and then I want to open it up to the audience. So the first question is, I mean, we're all aware that these are very uncertain times for federal funding. You talked about how you struggled originally to get federal funding for your work, but then were successful. How can we ensure an innovation pipeline in this moment when funding from NIH or NSF is far more insecure?
Yeah, well, I mean, I don't have any magic answers. I think people throughout history have done innovation. I mean, way before there was the government. I think Sputnik, starting in the 50s, would really galvanize the government to, fund a lot of things. But innovation and World War II, there was, but I think that people, people have lived through wars, they've lived through other things, and people keep innovating. I mean, sometimes they're harder than others, but, people ultimately prevail. Obviously, what's happening now will, maybe take a step back, but I'd like to think, that ultimately, even if things are harder, people will keep innovating, and you know, you keep trying.
Finally, what are you really excited about now in terms of research or new ideas? I believe you may have something in your back pocket that.
Oh well, I could do that. That's a magic trick, but that wasn't actually going to be what I was going to say. It's actually not about. I mean, I probably could do a magic trick, but at any rate,
I think we'd all like to see that.
actually, well, I'll have to, but what I was going to say is the things in our lab that I'm excited about. We're doing a lot of things, you know, on, you know, creating new tissues and organs, you know, like we're working with Li Wei Sai at MIT, and I have this really great postdoc, Alice Stanton, who Mass General and Harvard Med School just offered assistant professor to at their Neurologic Institute, and she's created like this brain on a, you know, real, like sort of, you can make personalized brains on a chip, and there's a whole range of
and so on.
What's that?
Organoids, or
It's not an organ. I mean, I wouldn't call it an organoid, you know, but I mean, it's like almost a mini tissue or organ. I mean, it depends how you define these things. The biggest thing we do in our lab today is actually we're working with the Gates Foundation. You know, Bill came to see me, it must have been about 13 years ago, and asked, well, could we take some of the things we've done in our lab and, you know, create things that could help people in the developing world. So examples are, you know, people don't come back usually for, you know, there's very poor, as bad as compliance is in the United States, it's much worse in the developing world. And so we've come up with pills that could last for a week or a month. We have come up with...
birth control pills.
Yes, that's one of them. I mean, they're still early stage. There's a number of things in nutrition. You know, people don't get enough vitamin A or iron, and so we've, you know, come up with new ways of incorporating that even in...
That's something Rhonda Zhang is working on, right?
That's right.
I think she's here, is she?
She won the Collegiate Inventor of the Year for for some of that nutrition work she did, and has a patent on it, and or with pending, and then vaccines. You know, we're creating what I call self-boosting vaccines. So you could just give a vaccine once, and maybe someday we're also working on ones that, you know, will be shelf stable, that you could ship all over the world, maybe make into little patches that you could just put on your skin. But there's a whole range, new kinds of children's medicines. I mean, we have quite a number of people in the lab working on these things, and we've set up companies as well to try to, or nonprofits to try to, you know, bring these forward. One of them will probably, you know, a way of giving vitamin A and to people in Africa, I'm hoping will be, you know, distributed later this year. We'll see. But at any rate, those are some of the things we're doing in the lab. What I was showing you before, we've come up with pills that you can swallow that I hope will be able to deliver orally, like insulin or messenger RNA or, you know, anything you want. And that was what I was showing you before.
Yeah. Do you think you could show it again? Or?
Sure.
Just for a moment, and then please put your hand up if you would like to ask a question.
Did I put it in my pocket? Yeah.
I think it was
yes,
in the back
I did.
pocket.
So anyhow, it's a little hard to explain all the things in it, but there's like a needle. The needle is actually, well, I'll show you. So let me show it first. Gio Traverso, who is now, he was a fellow with me. He got his postdoc with Bert Vogelstein, and now he's a tenured professor in mechanical engineering. And some of my other students, Alex Abramson, really developed it. But this little tiny thing, and
it's quite tiny. You may not be able to see it from the back, but it's.
But at any rate, so the idea is there's. I'll hold it like this too. There's like a little needle in it, inside it. The needle is made of. The needle is almost pure drug, though you could have some excipient to make it hard enough. And behind the needle, inside this, by the way, there's a little hole here, so the needle will, as I'll go over, come out. And then behind the needle, there's a spring, and it's cocked, and it would shoot, if it was released, it would just shoot, the spring would just shoot the needle right out. So if you swallowed it, you could make that happen, but you don't want the needle to come out right away. You really want it to come out in the stomach. Gio actually, even though he's in the mechanical engineering department, is actually a gastroenterologist. And you know, he would say, like, if you look at the stomach, there's very little pain sensations there and heals very quickly. So and people have gone, like all the time, people have had what is called endoscopes, right, where you go in through your rear end and you can do operations in the stomach and it works fine. Our idea was, well, maybe rather than going through the rear end, you go in through the front end and do something in the stomach. But how do you do that? So the idea is you have the needle, behind it's the spring, so you want it to come out in the stomach. But that's probably take an hour to maybe get there. So what we do is we embed that spring in a glass, except the glass we make is made out of sugar. So you have this little glass, and what happens is there's something called osmosis. Water will come in, and it'll break that spring. But depending on the thickness of the glass, it'll take, well, whatever time you want, but we make it be an hour. So anyhow, the idea is you swallow this thing, and it travels into your stomach, and then the water comes in, and it breaks the glass and shoots out the needle right when it's in the stomach. And it's really fast. We have videos of it. But the one thing you might ask, and the spring, by the way, is too big to get out of this, and the needle gets out when it happens. And it's like I said, so it's an injection. Rather than injection in your arm, it's an injection in the stomach. You might ask, well, how do you know that the needle, that this is always going to be face down in the stomach? So we modeled it after what's called a leopard tortoise. It's also like a Weeble Wobble toy, and it will always end up like that. I'll just do it, but then just to prove that it's not just me, I'll see if I can get a volunteer. So would somebody like to try, and does anybody want to be a volunteer? just to make it look. So the question is, yeah, so you can shoot it, but make sure everybody can see. No, they'll probably see it better up here. Yeah.
Did it work?
It'll always work.
Is it injecting the
We've
floor?
done it thousands of times. And Gio's come up with other, thank you, that's all you're doing. So Gio's actually, come up with other ways. He's got one like a squid that shoots it out, so you don't even have to have a needle. And, now, and Novo Nordisk, has helped us. They've actually done 65 patients with just water in it now, but, it looks to be safe. So, and we've published papers, at least in animals, not only showing safety, but that you could deliver everything from insulin to antibodies to messenger RNA. So anyhow, that's
fascinating.
I usually do card tricks.
We could have that later, but let's have some questions from the audience. We've got some amazing people here. We would love to hear from you. Yes.
Can you say something about what sparked your interest in magic?
We have a fellow magician here, I believe. Yes.
Yeah. Well, it's a good question. I think maybe even that chemistry. I've always loved card tricks. I used to love to watch people do tricks when I was a little boy. But actually, the chemistry set was really good. I'm sure lots of people know this. You could put something like phenolphthalein in water, and if you depending whether something's an acid or base, it'll change color. And I just always liked that kind of thing. It just fascinated me.
Great. So any non-magic questions? Yes, Phil, please.
So one of the most impactful pieces of your work is with Moderna delivering messenger RNA. Can you, and rescuing us from a pandemic and to a point where we could go back out in society and intermingle and work. So can you give us a description of that journey?
Sure.
And just how it evolved.
Yeah. Well, again, really, thank you, Phil. First, it's many, many people that deserve credit for that. Just in terms of my own journey, we had shown, and I'll start with the academics, and then I'll get to the company. So academically, in 1976, that was the first time anybody had shown that you could. And people didn't think it was possible, but that you could deliver a large molecule. We had put nucleic acids in these particles and showed that could happen. But still, when you make little particles, lots of other problems occur even though you could deliver something from it. One of the problems is when particles are so tiny, they aggregate, and macrophages can eat them. So ourselves, working with Vladimir Torchlin and other people, we took actually something that's in Miralax. Miralax is, if you need to go to the bathroom, it's polyethylene glycol, and it makes things very hydrophilic. So we came up with coatings, it was published in Science, that make that much harder to happen. And then we both looked at polymers and lipids. We actually started, the first paper on vaccines was also in the 1970s, and that was with polymers, but then a few years later we did it with lipids too. But then you could do, if you use polymers, you can use a single thing, but lipids, liposomes, and people also call lipid nanoparticles, depending on what you do. There are actually 4 components. Polymers usually 1 component, maybe 2 if you put the polyethylene glycol on. So here, one of the challenges is when you use the lipid nanoparticles, there's people had shown in the late 80s that certainly if you're going to use a nucleic acid, you want to use something cationic. People had done that with polymers and lipids. But if you did use something cationic that was charged, it might cause toxicity, and your complement activation in particular. And then the second problem is you need to get it out of the endosome. So I had a couple of postdocs in 2000. Dan Pack came from Francis Arnold's lab and now is at Kentucky, and David Putnam, who is now at Cornell. And they actually created what we call ionizable materials, or used ionizable materials to address that problem. So something would start out neutral, but then by adding something to it, but then, and because it's neutral, it doesn't cause a toxicity. When it gets into the cell, because of its what's called PK, it becomes charged, and then it gets out of the endosome. And there was good work also out of Vancouver, Peter Cullis's lab, that did that about a year later. Then the next question is, well, what lipids do you use? And and one of the things that Dan Anderson, when he came as a postdoc and was in the Koch Institute, did, and actually did with Alnylam, with Ken when he was there, is come up with ways to make thousands of lipids. And so you had the idea, because before that time there was maybe only about 40 lipids that people used. So now you have the idea that you can maybe choose these. And then I had another postdoc, Rohit Karnik, who now is in mechanical engineering, and he developed ways of using microfluidics to make different nanoparticles. So anyhow, in 2010, Derek Rossi came to see me. He was at Harvard, and what he had shown was that you could take the Yamanaka factors, and rather than use viral vectors to change a stem cell into a regular cell into a stem cell, you could use modified RNA. And he was interested in starting a company. And he had maybe 3 ideas mentioned to me, that maybe you could have one that would make reagents, maybe you could do something in stem cells or tissue engineering, or maybe you could make proteins. And so and he had tried to get funding actually from Third Rock and others, and they didn't do it. So I said, geez, I think we could do it. In fact, I once used your quote. People usually say, why didn't people think it could be funded or done? Biggest thing is delivery. And I think you have a quote in 2007 that said that that's one of the big problems. And so I thought we could hopefully solve that problem. And certainly we'd made progress by that time in 2010 at Alnylam on things like that. So Derek and I, the next thing we did is Tim Springer had also, he told him to talk to me, he told him to talk to Nubar Fay, and so we talked to Nubar at Flagship, and he said, well, he'll fund it. And then we also got Ken Chen, who was a cardiologist, and so that's how we started. And then we got, to create a company, of course, you need a good CEO, and Nubar knew Stefan Bancel. And I actually had known him too, because I'd done some consulting, and Nubar said, well, can we convince him to come? And then we just kept getting more and more great people, many, many from MIT. By the end of 2019, we had, quite a few people. Stefan did a very good job raising funds. And what happened was we had, I think, 13 products in clinical trials, early stage, and then COVID hit. And, and Stefan, talked to people at NIH and other places and said, this is now in January and we should work on this. So, it's really pretty amazing. The Chinese had the sequence of the spike protein, and so that was published, and we actually just took that, and it took less than 2 days to actually design the mRNA, then less than maybe another month to put it in nanoparticles, and then another month to actually treat the first patient, which was in Seattle in the middle of March. And, really went on from there. The phase 1 trials were announced in May, and then there was BioNTech, which they started a little bit later, but they were working with Pfizer, and by the end of the year, both of those would get approved and get used all over the world.
The BioNTech delivery mechanism, was that similar?
It's also a nanoparticle. Yeah, they're similar, and and they build on the papers I mentioned by us and others, and they worked actually with that Vancouver group who I mentioned, I give them a lot of credit too. I mean, it's interesting to me.
Amazing story.
And to me, I always think it's a tremendous example of why startup companies are so important. No big company in the world would touch messenger RNA therapeutics until Pfizer started doing a little bit of work with them in 2018, but with BioNTech. And really, if you didn't have those two little tiny companies, BioNTech and Moderna, over 50 companies tried to make these vaccines, and nobody succeeded anywhere near like this. And so it really is a tremendous, when people say, like, big companies could do it. I mean, in so many of these examples, it's these little companies. Alnylam is another great example where people, which Phil started, if those little companies don't take a chance and investors and scientists don't take a chance on these things just don't happen.
Yeah, you've said elsewhere that sometimes the big companies, they'll just do a couple of experiments and then they maybe give up quite early, as opposed to the startups, which will really, walk over dead bodies to make it happen.
That's right. I mean, for me, just to give an example or two, for me, when I first started doing this in the 80s, we did get two large companies starting, and then we got grants, and I got a consulting fee, and I was very excited about that. But they gave up after a year or two. And then, I started Enzotech, which merged to form Alkermes, and Alkermes now has quite a few products based on these kinds of things. I think probably even a better example today, though, is, there was work done at Mass General Hospital on what would lead to GLP in the early 70s, and I think there was a company that started, Jeff Fryer, who was dean of Harvard Medicine, wrote an article on this, and that people tried to get they tried to get Pfizer to do it, and they gave up. I mean, now of course they're doing pretty well. That product does pretty well.
Yeah, definitely. Yeah, the question here, yes, up there. Yeah, thanks.
Hi, I admire your work a lot. And I noticed you just mentioned the role of Chinese researchers finding the sequence for the spike protein, and also the importance of startups in developing new therapies. Especially in today's context, I wanted to ask you, how do you view, or what's the current perception in the biotech industry of how startups in China are making progress in clinical trials, lower leasing fees, and also how they have a larger sample population, and how do startups in here, especially in the current context of funding and also kind of a lack of scientific trust, how do you view the competition going on in the long term, and how do you think it's going to affect startups in the US?
Yeah, there's a lot to unpack in what you asked. That's not a criticism. So I think, I'm not sure I know how many great startups there are in China, but there's a lot of really good work going on in China that obviously has a giant impact, and there's certainly lots of companies in China, doing good work. I always think that in the United States there's been a tremendous amount of innovation and taking risks, and I think there's a number of startups that have done well, but this is a tough time, the last 4 years or so, or last 3 years for biotech companies, and of course the last couple of weeks have certainly not been so good either. But I still think that like in the long run, I mean, some will be successful. I certainly think, I've seen biotech go through ups and downs, and I think that will continue. I don't know when the next down will be over, but I fully expect with all of the tremendous work that goes on, some good things will happen. But I don't know, it's impossible for me to predict when, but I still think there's just a lot of great work going on in these companies. But the last several years have been very tough. Lots of them have gone out of business. The stocks a lot of times have gone way down. And right now, maybe much harder in the next couple of years but we'll see. I don't know. I still expect there'll be some good things that'll happen.
Do we have a question at the front here? Yeah, please. Nice T-shirt, by the way.
What advice would you offer to a kid who wants to be a scientist and invent things that will help people like you did?
Well, I really think the most important thing is to get a good education. That's the number one thing that I think. And actually, I would even stress early on, learning fundamentals, and then maybe probably working with good people. But I still think when you're young, even I'd say this to undergraduates, which is probably a few years older than you, that really learning the fundamental things, really learning fundamental biology, chemistry, physics. I think that's the most important thing, to do.
Thank you.
Thank you.
And there's a question behind you there. All right. I think just here. Yeah.
Hi, sir. First of all, namaste from India. I am visiting first time USA, and I just got successful exit from my first startup, and now I am very much interested in science related stuff, and my wish is to build BlackRock for a science to give funds and encouragement to the entrepreneurship for especially research related thing. So my question is for you, that you have experience in science as well as entrepreneurship related things. So how can I take my first step to build those kind of thing? Last week I had discussion with Jennifer Doudna, ma'am, who got Nobel Prize for CRISPR. So what is your thought about my big dream and wish?
Well, she would be a good person to work with.
Yeah.
But, I think to me, it's finding something, and again, I don't know enough about your education and everything else, and, but to me, it's finding something that's important. I personally think if you, in the medical area, having patents are very important so that you have that and that you have really good people to work with. So I don't know that there's any, and if you haven't been in, a biotech company before, maybe, learn by being in one of them. I don't know, I'm probably a little too overcommitted.
One more question. Oh, I see two more questions. I think we have time for just two, and that's probably, we're going to have to gradually wrap up. Thank you.
Okay, thank you so much. My name is Liz Hong. I'm doing AI in medicine, and I've been launching a startup which is utilizing electron model to analyze medical data, which has been piloted in the hospital. So my question is, which is also arranging as my research, but there is a challenge as we have to face to is that I haven't been to business school, and I have to learn how to recruit people. I really want to recruit people who is much clever or smarter than me. And sometimes I find that money isn't enough. So as a co-founder of so many successful companies, also a good leader professor of an academic lab, Could you please share some tips how to recruit people who are very smart and create an event which can bring out everyone's best? Thank you.
So I think you're in the right place coming to MIT if you want to recruit very smart people. You know, and Boston is a great place to recruit very smart people. I think that, to me, it's like having a project or program that really can be powerful and can have great impact. And so if you have a program, you know, like just mentioned Jennifer Doudna, you know, so say you have something where, you know, you look at the work where she did, which enables you to do gene editing. If you work with people, maybe find somebody or yourself who's, you know, made a great discovery, you know, that, and maybe the way to start with that is work in a venture capital firm, actually, for both of you. You know, if you're able to get some job as a resident somehow, because they see an awful lot of things, you know, and the way you attract people, if you have a great vision, I think that people usually do these things for stock. That's more important than cash. You know, when Genentech started, I remember the story, there was a guy who was a high school student, and Genentech gave him a summer job, and they said, well, we don't have any money to pay you. So he took stock, and this was in the 1970s. And when Genentech went public, he made $4 million. So I think that stock is ultimately, you know, people understand that. And I think people do things because they want to do good. They have a passion for science, and they have a passion for using science to make a difference in the world. And if you convey that message, you know, appropriately, I think that gets them excited.
Final question, yes. Oh, sorry, two, okay, well, I did promise him one, so I'll give, you can both have one. Beth, please.
Mine was a good concluding question. I wanted to say, first of all, thank you for the work you've done. And second of all, thank you for being here, inspiring the audience and those of us here. I lead the Kendall Square Association, and I can't tell you how many press calls we've gotten recently about the current state of affairs. And I would love to make one more ask of your time, very small, which is to help us make the case of the importance of academic research to lead to the development within startups and corporations that eventually will reach patients. If you could help us make that case, that would really go a long way.
Sure. Well, I try, you know, and I hope we can make that case. I think that's super important. I agree with you. And of course, Kendall Square, you know, that's really just been an amazing place for all these startups.
Just a very quick question. Yeah, the microphone is coming. So.
Really inspiring talk. I was wondering if you could just talk a bit about the creative aspect in science and maybe your own ideas for idea generation and I guess where good ideas come from.
Yeah, well, I think it depends on they come from all over the place. I mean, sometimes, you know, there's different ways that I see it happening. I don't know that there's any one way. For me, you know, I personally feel I was very fortunate in a way that I knew something about chemical engineering from my, you know, studies, and then working in the hospital, I learned something about surgery and medicine, and I've developed odd ways of sometimes putting them together. I mean, just to maybe give an example, I remember I had to give a talk to the American Heart Association, some dinner speech, but I got there a little early, and I, you know, always like to exercise because I end up eating too much at these things. And I got on the bike, but I always want to have something to read when I'm on the bike. So I picked up a magazine, and I think it was Life magazine, and they were talking about cars of the future. And one of the things, this was quite a number of years ago, and when they were talking about it, they said, well, you know, car of the future, let's say it gets in an accident and there's a dent. All you'll have to do is heat it up, and it'll snap back into place. And what they were talking about was shape memory metals, which are metals that if you make them a certain way, and you then give them the right trigger, they will memorize what shape they were in and bounce back. So I thought to myself, well, maybe we could make shape memory polymers, and that might be useful in an area like minimally invasive surgery. And so the idea that I was thinking about, I mean, again, this hasn't come to pass yet, but we did publish a number of papers on these. Andreas Lindlein, who worked as a postdoc with me. So like just to pick an idea, let's say you had to do an operation, and now there's, you have people do minimally invasive surgery, and let's say you wanted to tie a suture knot to do some surgical operation. Well, maybe what you'd be able to do is just make this hole, put the string in the hole, and then if you had to tie up a certain thing, it would just it would do it automatically, so that you wouldn't have to do a major operation for certain things. And so, but there are many things like that that you could, put, that when I look back that we've put together. Other ways that we've done it is like you have an idea, like what I mentioned, creating new polymers that could help in certain medical things. I've gotten together, chemists, biologists, we sit around and brainstorm and write formulas on the board and think about, well, what monomers might work, what bonds might work, and try to come up with something that'll have certain properties, and then try to make it. But I don't think there's any one way. I think there's multiple ways depending on what you're trying to do.
Fantastic. Well, I'm afraid that's all we have time for. I really want to thank all of you for joining us for this amazing discussion, and what an extraordinary story of impact, of persistence, of innovation, and of relentless curiosity as well. I mean, I think this really comes through in everything that you've shared with us tonight, Bob, and I really want to thank you most of all for really engaging in this very frank and open discussion. And I think all of us are feeling very inspired, and we need a bit of inspiration in these times, so thank you for that. We truly appreciate it.
Thank you. Thank you. Thank you for having me.